Hi class. All right, we're going to try this again with my microphone. Hopefully this improves the audio quality, or with my headset. So in the last lecture we covered sample covariance and sample correlation. So in this lecture we're going to see how to use that in practice. So again, we're looking at two-dimensional numeric data. It has to be paired. I have another example here, such as people's weight and height. It's paired because it's about one person. If we were to measure people's height and people's weight, but they weren't lined up, or it was one group of people versus another group of people, obviously it wouldn't be paired. And so, like we discussed in the previous lecture, it's paired if it's coming from the same sample space. So imagine that we have the sample space of people, and every time we measure some number of things about a person, like their weight, height, age, gender, etc., so their weight and height are sort of sub random variables or sub pieces of this very large sample space. Okay. So in this example, we're going to look at a data set called the IRIS dataset. It's a commonly used data set, and it describes some information about iris flowers. And they look at sepal length, sepal width, petal length, and petal width, and species. So I learned what a sepal is from this. If you didn't know what a sepal is, we'll see it in just a second. It's kind of like a petal. So there you go. There's the petal, and then there's the sepal. Wow. So to get started, we're using PyDataset again. So we will import PyDataset, grab the iris dataset, and turn it to a matrix. So the line of code there with the, I really want to be able to see my cursor, so I'm going to make my cursor visible again. So this turns it into NumPy data. And then we're going to remove the species. So obviously, if you were going to look at this data set seriously and study it, you might want to look at sepal width and petal width versus species. But we're going to remove that. So I'm just going to follow along in the lecture because why not? No module called PyDataset. So if you see this, you can just install it. I think you would need to add -- user, but I'm going to avoid that for me because I don't need that. Okay, and I need to restart my kernel, so I'm going to open this back up. All right. And so let's take a look. Ah, interesting. It looks like there's an updated version, so we can no longer use that. So I'm going to try this. Nope. So now we will learn pandas get numpy array. They changed it to be values. Okay, because why not? Because why not? All right, so there we go. I'll have to update the lecture. So here's the data of sepal widths and petal widths in centimeters. Okay. So we're going to look at sample covariance, right? That was the point of this lecture. So we can use the numpy.cov, and just like the standard deviation function, we're going to add this deducted degrees of freedom, and that basically puts that n-1 in the denominator. Okay, and this is that covariance matrix format we saw, the sample covariance matrix format we saw. So if you remember this from last lecture, it shouldn't be anything to learn about it. So let's see. So in that example, I was looking at the first and third column. Right, so then we have our nice set of covariance matrices. And you could actually add more, I believe. Let's just give it a try, see what happens. Looks like there's maybe a little bit more to it. So if you just give it the whole thing, it'll do everything with itself. So here's a complete covariance matrix of everything with everything. Anyway, it looks like we will just be doing it though with one random variable with another random variable. So we'll just be looking at 2 by 2 covariance matrices for now. So here we go. This is what I wanted to know. So if you put this in, we will get the complete 4 by 4 covariance matrix. Because remember, we have petal width, sepal width, petal length, and sepal length. Let me just make sure that it's length. Yes, length and width. Okay. So we saw if we put in 2 columns of the data, we get the 2 by 2 covariance matrix. Then if we put in all of the data, but put row var equals false, it gives us the covariance matrix of each column with every other column. Now, why do we have to put row var equals false? Well, by default, it assumes that the rows are the random variables, but in our data, the columns are the random variables, right? So each row is a new flower, a new iris, and each column is the random variables. So you can see this really kind of follows the idea of paired data. So when we look at the data, this is one iris, this is one iris, this is one iris, right? And these are individual measurements inside of the iris. All right. So if we look at this matrix, it's sepal length and sepal width, petal length and petal width. So we can see which of these maybe are connected. Okay, so if we look here, we can see that, so remember this is going to be sepal length by itself. So this is the variance of the sepal length. Then here's sepal length with sepal width. So you can see if it's a little bit wider, then it's a little bit shorter. See, they're anti-correlated a little bit, or anti-covarying. Then if we compare sepal length with petal length, they covary. So if they have longer petals, they have longer sepals. Okay, but one of the things you might be wondering is how strong is this covariant? Because we have the internal variance, right? Some of these things have a lot of variance, and then we have the covariance. So that's where the correlation is going to be more useful. Okay, so before we do the correlation, we're going to look at a scatter plot. So this is just sort of, if you just try to plot these things, like we want to see a couple examples of lengths and widths, or this is sepal lengths and petal lengths. If you do this plot, you get this kind of weird bunch of lines. And that's because Matplotlib is trying to draw lines between all the points, but there's no reason to draw lines between all the points. They're just points. So if we do this a little bit more intelligently, okay, looks like this. And here's the data. So you can kind of see they might be correlated, right? As it gets longer sepals, it might get longer petals. And the actual covariance of these things, it's 1.27. So, that seems like a large value. So maybe there is a covariance. Now, if we look at this other plot, the petal length versus petal width, you can see that they also appear correlated, like as one rises, the other rises. But notice that the covariance is smaller. And that gets at this thing that covariance measures correlation and the variance. Okay. So, a low covariance or a high covariance doesn't necessarily mean that they're correlated or not. So this is where the sample correlation becomes more important. All right. So again, we can use this kind of format here, but now we've used core_coef. Okay. So let's go ahead and start looking at the correlation. Oh, we don't need this. So here, oh, by the way, why do we not need deducted degrees of freedom when we're calling correlation? Because if you look at the expression, this one has a 1 over n minus 1. This one has a 1 over n minus 1. So the n minus 1s cancel, and it no longer matters. So that's why you don't need it. Okay. And here the diagonal is obviously 1, right? Because the correlation of anything with itself is 1. But here we can start to see how strong these correlations are and see that this one we thought maybe was important here. It's actually, almost no correlation, right? A correlation coefficient of 0.1 is almost meaningless. But these ones are very, very correlated. Okay. All right. So maybe we can just plot some of these things. Maybe we could, look at, what, why not do a little bit of programming? I'm doing this live, so why not attempt to do some programming? Let's make a plot of every single item here. So let's go ahead and put some names on these things because I keep forgetting them. So we have sepal length is the first one. Sepal width is the second one. Petal length is the next one. And petal width is the last one. Okay. So let's go ahead and look at some of these things. This one versus this one. Just doing some string formatting here. So I'm going to put in, the first one with itself. So names I with names j, and then we're going to have the correlation coefficient. So I'll set this to a variable so I have access to the correlation matrix, and we'll do this. Okay. X label names I, Y label names j. Okay, so this should now plot every single possible correlation as soon as we import matplotlib. Okay, so here's sepal width versus sepal length, which has this low correlation. And you see when we're looking at the data, there is a low correlation. This is sepal length, petal length versus sepal length. And this one is a little bit more correlated, and that's reflected here. Did I get these in the right order? This versus that. J. Yes, okay. Then here is petal length versus sepal width. That's interesting, a negative correlation. So as the petals get longer, as the petals get longer, the sepals get less wide, more narrow. Interesting. Okay, so here's all the correlations. Now, just because, I want to show you how to do this properly, what you could do is you could make a large plot of all of these together. Okay, so let's do that. Let's give that a try. So I'm going to make a plot of this. So we'll make a 4x4 subplot. And we'll make it a little bit big, okay? Because I want to show a big plot, Let's make it big. Let's make it 8x8. Yeah, just go 12x12. We'll go big. We'll go big. So now instead of, we're going to plot it like this. So this will make a bunch of little plots for each one of these. And it's weird, but you have to put set X label, set Y label there. Don't ask me why. It's just one of those things. That when you're talking about individual plots, you have to put set. So when we're working with individual plots, so when we have lots of little tiny plots. Let's take a look. Oops. Get those backwards every time. I think I get those backwards every time. Let's take a look at the documentation here. Returns fig, then ax. Okay. Let's take a look. So we only plotted them a couple because my for loop, I changed it. There we go. Okay, so now we have everything plotted. Notice these ones have a perfect correlation because they're on the axis. Okay. I might actually just skip those plots. So if I equals j, so it's one on the diagonal, we will just skip those plots. Okay. All right, then the last thing we need to do is lay them out so the titles make sense. And there's this nice command called tight layout, which will push everything apart so that you can actually read it. The titles still don't look so good, I think that because the axes here are labeled, I can actually omit this long part of the title, and we'll just put the correlation coefficient on there. There we go. Looks pretty nice. can put down, that this is the correlation coefficient. So, this is kind of interesting though. Like, do you see some of these here? Like this one has a correlation coefficient of 0.43. And, I think this is about as correlated as this one, which has a correlation coefficient of 0.12. I honestly think I would say these are the same correlations. So it looks like this correlation coefficient doesn't tell the whole story. That brings us to the last part, is a little bit of caveats here. So this is just a same kind of plot that we were just looking at here. So we have an X and a Y, and you can see that here I have sampled random numbers. So these are completely random. No relationship between these two random variables, but the correlation is about 0.27. So just looking at random numbers, correlation, if it's, 0.27 with the random numbers, that sort of gets at this law of large numbers. If we had an enormous number of numbers, like if we had sampled 1,000 or something, and 1,000, the correlation coefficient would approach 0, which is what it should be. But with a small amount of numbers, we don't get the law of large numbers telling us that sample statistics match what they should be if we knew everything. So obviously, if these two things are independent, that is, they're not related at all, the covariance would be 0 and the correlation would be 0. But we don't see that working when we only have 15 of them. This is sort of another kind of caveat. So this first caveat is that with a small sample size, it's possible to get spurious correlations. So small sample size, we can get correlations of 0.27 when they are meaningless. Another caveat of correlation is that sometimes you can have something which is definitely correlated. Like these two numbers are highly correlated, x and x squared, right? They're correlated. Like if I shouldn't say correlated. They're related. Like if you knew this one, you would know what this value is. If you knew what this x value was, you could compute this y value. But the correlation coefficient is low, 0.11, even though these things are not random, right? They're completely dependent. Once you know one, you can tell what the other one is. But they have a low correlation. So correlation only measures linear relationships. So if you have a nonlinear relationship like x squared, you'll miss it with correlation. So remember that correlation only tells you about linear relationships. All right. So correlation, very good tool for connecting two random variables, with data. Like in this iris example, very nice to get some insight into different, relationships between our data. But correlation is not perfect, especially when you have low numbers. So if you see numbers like below 0.5, you should think nothing of them. It means you don't know. Correlation also doesn't capture nonlinear relationships. Okay, so if you think about this picture here, is that this picture shows that correlation doesn't tell you the whole story for nonlinear data. But it's always a good first step. Just like how if you have some data, the first thing you want to do is compute the median and the covariance or the variance. Same thing with sample correlation. If you have two pairs, or sorry, if you have pairs of data, if you have paired data, the first thing you want to look at is correlation. Like you can look at correlation of weight and height. You can look at correlation of age or gender with weight and height, because it tells you about the relationship between them. Okay, so that covers lecture 4, and this whole lecture, this whole unit 7, was sort of summary statistics of data. So recall that in lecture 1 we saw we can compute the mean and the median, and then we saw in lecture 2 how to plot one-dimensional data. So that was looking at things like histograms and looking at violin plots and looking at what was the other thing? Oh, kernel density plots. And for two-dimensional data, our sort of tool of choice, our weapon of choice for two-dimensional data is always a scatter plot. Okay, always this nice scatter plot gives us a lot of insight into the data. And then our statistics we look at are sample covariance and sample correlation, with sample correlation being much more common and typically more useful. All right, so that covers the lecture, and that covers Unit 7.